Hello, thank you for the opportunity to speak at the IEEE Flaps Conference 2021. My name is Andreas Tröls and I work at the Institute for Microelectronics and Microsensors at the Johannes Kepler University in Linz, Austria. The name of the talk I will give you today is Optimizing Heater Electrode and Temperature Distributions on Large-Scale Sheet Metal Heaters. So first of all, why would one need special design temperature distribution? A few examples. Already existing works pay attention on, example given, special hot plates like this here, where you want your temperature to be as homogeneous as possible inside the heating area. This can be important in various lab-on-a-chip applications where we want to manipulate and move liquid droplets on a very small scale. It is commonly known that mixing fluids is very difficult in the microfluidic regime. There we have only a laminar flow and therefore we could build mixers which rely on temperature gradient induced flows which result from certain heater geometries like here. One can also imagine small fluid reservoirs where a paraffin valve opens and closes depending on the temperature of the paraffin. And the reason is that the surface tension and so the shape of a liquid is temperature dependent. The main goal in my work is the heater design for droplet manipulation by temperature-dependent surface tension, like you see in these pictures of other works. There, for example, here, a droplet can be moved around due to different line forces at different positions on the droplet. And this formula on the left-hand side here shows the force per length which acts on the droplet's triple contact line, emerging from different contact angles on opposite sides of the droplet due to a local manipulation of the surface tension. For that, we need a temperature gradient along the droplet's interface, and the presented work aims to design a heater system where the heater electrode positions are optimized for various temperature distributions and therefore various droplet operations like droplet moving, splitting, mixing, or merging. And because we use steel as a substrate for the heater electrodes, I call this lab on steel, contrary to the common lab on a chip term. So first we have to think about which liquid is most suited to be manipulated by a change in surface tension along its interface. For that, we have to take a look at the temperature-dependent surface tension gamma. There are a few semi-empirical relations to calculate the change in gamma with temperature, and the table on the left-hand side in the slide shows the surface tensions at room temperature for various liquids. And if we consider a linear change with some measured reference values, we get to this linear relation between the surface tension of a liquid and the temperature of the interface. If we plot now this linear relation between the surface tension and the temperature for all the liquids listed in the table, we see that water shows the highest dependence on its surface tension on a change in temperature. So gamma gets generally lower with rising temperature. And gamma's unit is millinewton per meter, so the change has the unit millinewton per meter in Kelvin. The right-hand side figure shows the same data as the left-hand side figure, but without mercury and only in the liquid region of water. There is also a nonlinear model from Schmidt et al., which I show here as a comparison. The difference to the linear model is not very big and does not change the fact that water has the strongest dependence, like we saw before. And this figure here shows the absolute error between the surface tension values of the linear and the non-linear model for the whole temperature range, from room temperature up to the critical temperature of the liquid. And showing the full range does not make much sense because water is liquid only in this small region here, and only there we can reasonably define a surface tension. So that's why this slide here shows the same data, but this time only for the liquid region of water. And the lowest deviation is in the region of gamma 0, because this is one of the reference points for the nonlinear model. And the maximum deviation here is about 2.5 millinewton per meter, where the slope of the linear model was about minus 0.2057 millinewton per meter in Kelvin. And now to our design. This slide here shows the steel sheet heater setup. It should demonstrate the possibility of the design for a precise temperature profile. And as an example, we use an uniform temperature profile. What do we have? We have a steel substrate here with width W total embedded in a polyurethane insulation. And on top of one insulation layer, we have screen printed silver electrode lines with length L heat, which are again covered by an insulation top layer. And the temperature inside this optimization area here should be homogeneous. And our goal temperature in this area is 333 Kelvin or 60 degrees Celsius. And this is measured at the bottom of the stack. The red optimization length eloped is the length along the substrate where the optimization algorithm optimizes for this temperature distribution by changing the distances between these electrodes here. And we therefore have a goal function f from t and x, which should be minimized for each point x, where x is the position along eloped. And the total integrated error is defined as the line integral of the goal function over the optimization length, so that the final optimized temperature distribution has a minimal integrated error. Like said, the minimization happens by changing the distances between these electrodes here, calculating the integrated error and shifting them again for an even lower integrated error. And this is done with the optimization module of the FEM solver in COMSOL multiphysics, and there we use a downhill simplex algorithm to do that. This slide shows a close-up of the FEM geometry here and the mesh in the region in between two heater electrode lines. This picture shows the same cut through the stack as the schematic in the last slide. And on the right-hand side, you see the simulation parameters for the heat transfer FEM simulation. And here on the bottom, you see the data of the mesh element sizes. I use a hybrid mesh consisting of a structured quad mesh in the steel domain and an unstructured tree mesh in the insulation and electrode domain. And the reason is because there the geometry will change during the optimization by shifting around the electrodes. This slide here shows the boundary conditions for the optimization. The lower boundary of the electrode to electrode distance di is, of course, when they are all in contact. So the sum of the center to center distances between the electrodes di has to be bigger than the width of one electrode times the number of distributable electrodes. And I start every optimization with a neutral uniform distribution like this, where the initial distances are calculated by this term here. And on the bottom, you see the boundary condition for the electrode distances for every following distribution during the optimization. And in the formula here, the factor 2 comes from the fact that the distribution is, of course, symmetric around a center electrode. And we only have to calculate the distance shifts for half the number of electrodes to save some computing time. And this works, of course, only for a uniform temperature distribution. This slide shows optimization results for 3 different optimization lengths of 4, 6, and 8 centimeter. The top row shows the temperature distribution along the total substrate width. The center row shows the quadratic deviation from the goal temperature, and always as an inset, you see the value of the total integrated error. And the bottom row shows the distribution of the electrodes to reach this temperature distribution from the top row. And we can see here, for each optimization length, the temperature is now homogeneous inside this optimization length. And the total number of distributable electrodes, in this case, was 25 for each optimization. This slide here shows the difference in the optimization results if A, the algorithm does not allow to shift the electrodes outside the optimization area, and B, if the electrodes can be distributed freely over the whole substrate. So here is an example for an optimization length of 8 centimeter. And this could make sense if we want to save space on top of the substrate for other electrode distributions in the neighborhood of the homogeneous distribution. And of course, the integrated error here in A is higher if we use this restriction. You can see on this slide what happens with a converged solution for the electrode positions if we change the width of the substrate. It's obvious that the integrated error is at its minimum at the substrate width for which we optimize the electrode distribution. For smaller substrates, there are rises and saturates for substrates much wider than the optimized substrate width. And again, like in the last slide, the error is in general smaller for optimizations where the positions of the electrodes are not constrained by the optimization length. So how can we describe now the obtained distribution mathematically? If we start at the center electrode and plot the distances from one electrode to the next neighboring electrode over the electrode number, we get the linear behavior of dropping distances. And this behavior is the same for different optimization lengths. The difference lies in the integrated error if we keep the number of the distributable electrode lines constant. And it's obvious that the uniformity of the temperature is harder to preserve for larger optimization areas or optimization length if the electrode number is held constant. And this can be seen in the bottom figure where the integrated error is plotted against the optimization length. The final slide shows a fabricated sample of the heater before adding the top insulation layer so that you can see the screen printed electrodes on top of the insulated steel substrate. And in these close-ups here, you can maybe roughly see the resolution of the used screen printing mesh. The conductive heat electrode lines are realized by screen printing conductive silver paste on top of sheet metal substrates with the pre-coated insulation and cured at 140 degrees Celsius for 240 seconds. The screen is fluted with paste and the heater structures are printed through the screen with a semi-automatic screen printing machine. And we use Electrode PF50 as silver paste to print these heaters. Finally, the lower figure shows an infrared measurement using a FLIR E4 infrared camera. The numerical temperature values have been cross-checked using a PT100 temperature probe visible on the left edge of the substrate. And we can see that the simulated temperature plateau of 60 degrees Celsius has been hit almost exactly. And we can conclude that the results are sufficient compared to the FEM simulations. And the uniform distribution is clearly visible within a certain error range. And the reasons for deviation could be a variance in the print of the electrodes or other involved layers and too small spatial dimensions of the sheet metal in Y direction. But we will address this challenge in future works. In summary, the steel substrate used in this work is advantageous for fast temperature response in heating and cooling due to its high thermal conductivity. Concluded, the present work addresses opportunities and methods which will assist for the future design and fabrication of a fully functionable lab-on-steel heater system as an alternative to the common fluid manipulation techniques in a lab-on-a-chip device. Thank you for your attention.